Ladies and gentlemen, welcome to this second year level course in structural geology that we offer here at Rhodes University in South Africa. This course contains 6 separate chapters, essentially on topics related to the brittle field, and it includes 3 more topical chapters on the fracturing process, on the Moore stress diagram, and on Anderson's fault theory, and 3 more chapters on the bigger picture of structures in the regional and plate tectonic scale related to crustal extension and to crustal shortening. The current video that you see here only covers chapter 1, the fracturing process. The other chapters you can find in separate videos. Fracturing and the presence of fractures indicates that the rock has failed under brittle conditions. You know, there are 2 principal ways in which deformation can be accommodated: the brittle and the plastic deformation. And the presence of fractures and fragments indicates that the brittle field applies. The formation of fractures like joints and faults indicates that a large-scale breakage of atom bonds has taken place, often along planar or semi-planar surfaces, but often also along randomly and irregularly shaped surfaces. And all that produces fragments and new surfaces in rocks that separate parts of the rock bodies that initially were coherent entities. We see here such an example, a cohesive cataclysite with angular fragments. They are cemented again together because the fragmentation here took place in the presence of a fluid phase, and from this fluid phase this orange material has precipitated, and that restores cohesion in this rock after this fragmentation took place. That is why we call this a cohesive cataclysite or a cohesive breccia. In other cases where there is no precipitation and no re-cementation of the fragments, we would talk about a incohesive cataclysite. What they have in common is the loss of cohesion along these fractures and the formation of either planar surfaces like joints or faults, or the formation of such angular fragments in brecciated rocks. Why do rocks fracture? It is a feature that most commonly is realized at relatively low temperatures, because at higher temperatures plastic deformation is more effective and efficient and can take place at lower differential stress than fracturing. But in the brittle field at low temperatures, rocks fracture because the tectonic loading exceeds their shear strength, sometimes also referred to as yield strength. These 2 terms are very similar, almost interchangeable. Smaller tectonic loading might cause elastic strain. Rocks have a certain, albeit small, elasticity. Elastic strain would be recoverable, but as soon as the yield strength is exceeded, permanent deformation will take place, and in the brittle field that would be fracturing. Tectonic load applied to rocks is typically measured in terms of stress, and the unit for stress are pascals. Pascal is 1 Newton per square meter, and in geology we usually use kilopascals or even more commonly megapascals as a measure of stress. The principal stress vectors, the largest, the smallest, and an intermediate one, are called sigma 1, sigma 3, and sigma 2. Sigma 1 is always larger or equal than sigma 2, which in turn is larger or equal than sigma 3, and that relative magnitude of these 3 stress vectors will define the state of stress, whether it is hydrostatic or non-hydrostatic, and it will determine the shape of the stress ellipsoid. Here we see a stress ellipsoid of a non-hydrostatic stress field. We see clearly here sigma 1 is larger in magnitude than sigma 2 and sigma 3, which are roughly equal in size. This is clearly a non-hydrostatic stress field compared to a hydrostatic stress field in which all stress vectors would have the same magnitude. In this case, the stress ellipsoid would be spherical. Stress is defined as a force acting on a certain area, and here we see an example of a cylindrical rock specimen that is subjected to a non-hydrostatic stress field. Along the long axis of the cylinder, the maximum stress is applied, whereas the confining stress acts from all sides. And let's assume here these confining stresses, sigma 2 and sigma 3, they are smaller than sigma 1. That would expose this rock specimen to a non-hydrostatic stress field. If that stress field is large enough, then the shear strength of the rock would be exceeded, which would form these fractures that we see here. In this case, these are conjugated faults, which in the orientation as we see it here would be normal faults, because the hanging wall block that we see here in the center would slide downwards along these fracture planes in opposite direction, because these are conjugated fractures. The important parameter here is the differential stress. The differential stress is simply the difference between the largest and the smallest stress vector. And we remember sigma 1 is always the largest, sigma 3 is the smallest, unless we have hydrostatic stress conditions in which all these stress vectors have the same magnitude. We see here some rock specimens that have been produced during such compressive strength tests, and we see here on the left hand side the original specimen, which has undergone substantial shortening and barreling, widening, lateral extension. The sample here in the center has responded to the shortening with the formation of conjugated fractures and some fragment zones along these fractures, and a certain amount of this barreling that we see here. The sample on the right hand side shows only minor fracturing and essentially has formed this barrel shape, so a uniform lateral extension compensating for the vertical shortening. This would be an example where the deformation was mainly plastic. In the center, the deformation was probably equally plastic and equally brittle. So pretty clearly here in the undeformed state, the differential stress was 0 because we require a larger sigma 1 than sigma 2 and sigma 3 in order to shorten and deform these rocks permanently, and clearly the two deformed samples have experienced a differential stress significantly larger than 0. Here we see a natural example of such faulting. We see here an offset of the hanging wall downwards along this very sharp fault surface, and the red horizon that we see here is a good marker layer, indicating that here the displacement is maybe 1 or 2 decimeters downward displacement of the hanging wall block along this normal fault. Here we see how the results of strength tests of deformation experiments are recorded. They usually record the amount of differential stress that is required to achieve a certain amount of longitudinal strain along the axis of our cylindrical samples that we just have seen. Here on the y-axis, the differential stress, so the difference between the largest and the smallest stress is recorded, and normally these deformation experiments are carried out under constant confining stress. That means sigma 2 and sigma 3 remain constant while sigma 1 is increasing, and that obviously would increase the differential stress to which the sample is exposed. Here on the x-axis we see the amount of longitudinal strain, that means the amount of shortening of the sample, and here we see how the sample responds depending on the magnitude of the differential stress. What we typically see in these deformation experiments is a first stage of elastic strain. That is a linear shortening that correlates with the magnitude of the differential stress. So if we see here this first part of the curve, a straight line, it reaches a certain maximum at which it stops being linear. You see here in the upper part the line starts to curve until it reaches a maximum point. That would be the elastic limit, or also called the yield strength of the rock. Then we see if further shortening takes place, a rupture point. This would be the point when the fracture actually is formed. After the rupture point, we see a significant drop in differential stress to the frictional sliding level along the now existing fault, the created fault. So let's assume we load the sample with 20, 40, 80, 100, 120 megapascal differential stress. You will see the rock will undergo shortening, perhaps by 1%, but if we would reduce the load again from 120 to 180 and perhaps 0 megapascals, this strain would be recoverable. The rock sample would re-attain its original length because everything that happened so far is elastic strain, and we know that from everyday experience elastic materials re-attain their original shape as soon as they are no longer exposed to any force. Once the yield strength is exceeded, rupture will take place. The rock will fail. It will fail along a newly formed fracture, and that point is called the rupture point. Once that fracture has formed, the shear strength will drop. It will drop to the level that is required to slide along the now existing fracture. And this is a very sudden process that takes place. As soon as the fracture is formed, it requires a much lower differential stress to displace the rock fragments along the existing fracture, because all that needs to be done is to overcome the sliding friction along these surfaces. That is in principle how rocks respond to increasing load. We find an elastic limit at a certain strength that can vary from rock type to rock type. We find a rupture and a sudden drop to the level of sliding friction, much lower differential stress compared to the differential stress that is required to form the fracture in the first place. We see here on this table examples for weaker or stronger rocks. A very weak soft rock will have a shear strength of perhaps 10 or 20 megapascals. These are often weathered or soft sedimentary rocks. Other rocks like schists or better cemented sedimentary rocks are a little bit harder. Typically coarser grained and igneous rocks are moderate in their shear strength, and the strongest rocks we will find amongst the igneous rocks, particularly fine-grained igneous rocks, can have a very high shear strength, perhaps exceeding even 160, maybe 200 megapascals. Here we see an example of such a strength test. We find here our specimen is put into a experimental rig that shortens vertically, and let's just look what happens. Here we see a fracture has formed. It is not dissimilar to the fractures that we have seen in our graphical examples before. This was a fairly simple setup. There are much more sophisticated rigs that can carry out such deformation experiments. Here we see some illustrations showing that an upper and a lower piston and the anvils are pressed against the specimen that we see here. Very often these specimens are covered in a thin copper jacket that hold the specimens together after rock failure, and upper and lower pistons are pressing them together with great force in order to fragment these rocks. Here we see a cross section through the whole instrument. We see here again the chamber with the specimen. We see here the lower anvil and the lower piston, and here we see a small inlet that allows to increase the confining stress. The confining stress, we remember, acts laterally onto the sample, and we can inject here fluids or sometimes salt that can provide this lateral confining stress, simulating conditions as they exist deeper in the Earth crust. Here we see results, samples that have undergone shearing, conjugated faulting, simple faulting, more or less intense barreling, and probably ductile failure here on the right hand example. These samples are still sticking in their copper jackets that prevent the fragments from falling apart. Fragments, of course, because the rock specimen, our sample, has lost cohesion. Here would be again the examples that we have seen earlier. There are two important types of test: the tensile strength test and the compressive strength test. What we have seen so far were examples showing results of the compressive strength test. The tensile strength test is also very often carried out because it's important, particularly for civil engineering purposes. The tensile strength is the weakest strength of rocks, and for engineering purposes, this magnitude, this characteristic needs to be known in many cases. The tensile strength test is simply a test on rock specimens with a laterally pulling force. That means we see here the smallest stress to which the sample is exposed, sigma 3, would actually be pulling, and conventionally such pulling stresses are given a negative sign. So sigma 3 in this case would be negative. All we do in the tensile strength test is a rock specimen is grabbed in our testing rigs and it is pulled laterally. The first stage of deformation would be a small amount of reversible elastic extension before in a second stage we produce mode 1 extension fractures, which follow a abrupt rock failure along fractures that are perpendicular to sigma 1. That is illustrated here. Roughly we see here fractures pretty much perpendicular to the direction of the sigma 3 stress vector would form. This sudden failure of the rock is a result of the coalescence of microfractures. We know that every natural rock material has already microcracks, microfractures, grain boundaries, so zones that are irregularly oriented, frequently are very short, maybe only a few hundred micrometers long, but some of them will be oriented perpendicular to sigma 3. And such microfractures would grow and eventually coalesce. That means they will merge, they will combine their length, and this is a process that can be self-enhancing and suddenly forms to rock failure. This coalescence of microfractures and rock failures forms joints, mode 1 extension fractures, and here we see what that means. A mode 1 extension fracture is simply the tensile opening of a fracture. The movement, which is much smaller than illustrated here, so this is an exaggerated illustration, is simply the opening of a crack with a movement perpendicular to the fracture surface. Now, that is what would happen if we laterally pull this sample apart. This process by which microfractures increase their length and lead to sudden rock failure follow the Griffith criterion. Here we see what the Griffith criterion means. It is an important process that explains the sudden fracturing of rocks when they are exposed to stresses exceeding their yield strength. Let's have a look at this Griffith criterion. We see here sigma c equals k in a square root over nu divided by 2L. What do these symbols mean? Sigma c is the critical tensile stress that is required to form fractures. That is simply the amount of sigma 3 that we need to apply in order to make the rock break. That depends on the physical properties of the rock, and these physical properties are encapsulated in the symbol K. That is a material constant which can be larger or smaller depending on rock type. Nu is the energy per area unit to propagate microfractures, and 2L is twice the length of pre-existing microfractures. So if you have microfractures that are already in the orientation of the future fracture, that means perpendicular to sigma 3, you will have to only make them grow until they transect the entire rock specimen. And when you look at this equation here, as soon as you start coalescing the microfractures that are already there and that are in the right orientation, perpendicular to sigma 3, you will decrease the stress that is required to make the fracture transecting the entire specimen. So simply as soon as microfractures start coalescing, we will start a self-enhancing fracture propagation, and that is the reason why rock failure is so sudden once you reach the yield strength. Very similar processes take place in the compressive strength test, and we have seen in previous slides some of the examples how compressive strength tests are carried out. We are now looking at a rock specimen that is exposed to compressive stresses from all sides. The smaller sigma 2 and sigma 3 act laterally, and sigma 1 again acts parallel to the long axis of the rock specimen. All side compressive stresses are much more realistic for geological purposes because as soon as you go away from the Earth's surface, all stresses will be compressive. There are factually no tensile stresses deeper in the Earth's crust, and that means for our interest as geologists, compressive strength tests are much more important than tensile strength tests. If you expose a rock specimen to a differential stress, to increasing differential stress, again, there is a first stage of deformation, and that is the closure of microfractures and pore space that is oriented perpendicular to sigma 1. So, for instance, pore space and microfractures that are oriented like this one, or like that one, or that one. Whatever opening is there and whatever pore space exists in this orientation, this pore space will be closed. And that is a first stage of irreversible minor shortening. If there is no pore space and only very limited or no microfractures in that orientation perpendicular to sigma 1, stage 1 simply is irrelevant. And as soon as we increase sigma 1 a little bit further, we will start with the elastic field. We will start with the elastic shortening that is illustrated by the linear part of our deformation curve that we see highlighted here. So imagine your differential stress increases, sigma 2 and sigma 3, our confining stress remains constant. What will happen is the material will start to shorten vertically and it will expand laterally. This is what we call elastic barreling. The amount of barreling depends on the magnitude of differential stress. So barreling at 80 megapascal in this example here will be more intense than at 60 or at 40 or 20 megapascals. And barreling will carry on increasing until we reach the yield strength somewhere up here. This is what we call a linear elastic body, or also called Hooke body, because it follows Hooke's law. And Hooke's law simply means that depending on the magnitude of the differential stress and capital E, which is Young's modulus, again a physical property of the rock, we will achieve a certain elastic shortening. So depending on the amount of differential stress, we will shorten the rock depending on the physical properties of the rock type that we investigate. We can rearrange this equation in order to determine Young's modulus, and Young's modulus is simply the amount of differential stress required to achieve a certain amount of elastic strain. Young's modulus is a number that you can look up for different rock types in tables, and for most rock types pretty reliable data for Young's moduli have been produced and published. Again, I would like to stress that we are still in the elastic reversible extension. The lateral bulging, this barreling of the specimen, can be undone by reducing the differential stress. So as long as we are here in the linear elastic field and we reduce the differential stress, we will reattain the stretched and unbarreled shape of the specimen down to a stage where its full initial length is re-achieved. What is important is that during this elastic barreling, this lateral bulging that we see here, we might find that microfractures that are parallel to sigma 1 start coalescing, because this lateral expansion here, that also creates some space as soon as microfractures start to connect with one another. And that is then the transition to stage 3, the formation of microfractures parallel sigma 1 and perpendicular to the confining stresses. That might lead to an irreversible dilation and to an increase in volume. And at low confining stress, that means when sigma 2 and sigma 3 are relatively small, we find that these microfractures parallel to sigma 1 start coalescing, and they form then tensile fractures. And these tensile fractures also follow Griffith's criterion. Again, as soon as we coalesce the microfractures, we will find an explosive propagation of tensile fractures perpendicular to sigma 3, and that is the same in principle like stage 2 of the tensile strength test. So we see here Griffith's criterion applies to both the tensile strength test and the compressive strength test. We coalesce microfractures in response to the lateral dilation in the elastic barreling stage. Now, if we imagine that the confining stress increases, that means the magnitude of sigma 2 and sigma 3 pressing against the rock specimen from the sides here, if that becomes higher, then the barreling, the lateral elastic extension, will be counteracted. And if we counteract the barreling in the elastic stage, we also counteract the coalescence of microfractures parallel to sigma 1, which have produced our tensile fractures on the previous slide under low confining stresses. So that is an important difference. When we increase the confining pressure, we have less barreling, and therefore we have less coalescence of microfractures that might form in response to that barreling. What we form instead are what we call transitional tensile fractures. And transitional tensile fractures are fractures that have an extensional component and a component of lateral sliding here. So the lateral sliding is indicated here along these conjugated two fractures that form obliquely to sigma 1 and to sigma 2 and sigma 3. But what is not shown here on this diagram, they also would have a component of lateral opening, of tensile opening, just like the fractures that we have seen for low confining stresses or the fractures that form in tensile failure under tensile strength test conditions. It is important to see that with increasing confining stress, we are changing the orientation of fractures from tensile fractures parallel to sigma 1 to transitional tensile fractures at an angle up to about 30 degrees between the fracture and sigma 1. This is the typical orientation of these transitional tensile fractures that form under compressive conditions and under increasing confining stresses. Here on this diagram we see kind of a summary of what we have been talking about. We see here 4 representative experiments under increasing confining pressure or confining stress, sigma 3, and we see here increasing differential stress is required to cause rock failure. That means not only do we increase the confining stress here from left to right, very small sigma 3 here, fairly large sigma 3 here. Once we do that, we also require increasingly large sigma 1s in order to make the rock fail. That means increasing confining stress will increase the rock's shear strength, and we can symbolize that by a stress ellipse. We see here under low confining stresses the stress ellipse is relatively small. That means the differential stress between sigma 1 and sigma 3 is not very large, but under these conditions is sufficient to cause rock failure. Mode 1, tensile fractures. Extension fracture is actually not a very good term. You will read that term sometimes in the literature. With increasing confining stress, as we just have seen, lateral barreling is increasingly counteracted, and we form transitional tensile fractures which have a component of tensile opening but also a component of lateral shearing. And this lateral shearing becomes more and more important until we reach a stage where we do not have tensile opening, we only have lateral shearing. That means mode 2 or mode 3 displacement along the fracture surface, but no tensile opening anymore, as we have seen it in the transitional tensile failure environment or in the tensile failure environment. We can illustrate that also in our stress strain diagrams that we have seen before. Here now we see the stage 1, which is non-linear. Stage 1 is the closure of pore space that happens to be perpendicular to sigma 1. So this is the non-reversible part of a compressive strength test. But then we come into the linear elastic domain, where we find here our linear increase in shortening, but that linear part would be reversible if we decrease differential stress again. We see here two examples, one for relatively low confining stresses, and we see here that the yield stress is reached at lower differential stresses compared to the same rock that has been tested here under high confining stresses. And so we see here, as we have seen on the slide before, with increasing confining stress, we need larger and larger differential stress to make the rock fail. That is illustrated here by a yield point at higher differential stresses for rocks under higher confining stress compared to those under low confining stresses. So if we carry on with this experiment, we reach our rupture point, failure occurs, and we find the drop to the frictional sliding level that is the residual shear resistance along the now created fracture. So the fracture that forms here requires higher differential stresses to form compared to the sliding that occurs along the newly formed rupture, the newly formed fracture. There are three possible processes. Steady state flow along that fracture would simply mean that with increasing strain, with continuous shearing, we remain at the same differential stress levels required to do so. Under some conditions, it's getting, during increasing sliding friction, more difficult to sustain the sliding. That is what we refer to as strain hardening. And that can happen, for instance, by fragments that start rotating and get in the way and need to be refractured during progressive friction sliding. Therefore we require, with increasing strain, increasing differential stress. More common is probably strain softening. Strain softening happens when we in some way lubricate the fracture surface. That can, for instance, happen by the presence of water, of fluids or groundwater that help to break down rocks along the fracture more easily, perhaps convert minerals into clay, and that makes it much easier to slide along the existing fracture. And of course, these same processes, strain hardening or strain softening, can take place at higher confining stresses. However, the important message for this diagram is here: after the closure of pore space and the linear elastic field, we come to the rupture point, to the failure point of the rock at lower differential stresses when we are at low confining stress, but we require higher differential stress if the confining stress is higher. If we translate that into geological situations, where would we find high and where would we find low confining stresses? Of course, the pressure increases the deeper we go into the Earth's crust. And that means high confining stresses we can expect at deeper crustal levels compared to shallower crustal levels. That tells us that the same rock at greater depth should be exposed to higher confining stress, and therefore also should have a higher shear strength compared to the same rock in a shallower crustal level. This indicates that with increasing depth, rocks are getting harder to fracture, as long as we are in the brittle crust. Here we see now a series of experiments. They are carried out at increasing confining stresses. Here the confining stress is 20, 40, 60, all the way up to 140 megapascals confining stress. That would mean the sigma 3 that holds together our sample and prevents barreling and coalescence of microfractures. And the response here is pretty clear. At low confining stresses, we find that this limestone failed at just over 200 megapascals, and thereafter we find a very significant drop to the level of sliding friction, a little bit of strain hardening here after 8% of strain, but essentially a fairly flat curve ranging at about 120 megapascals that will require to realize sliding friction under these low confining stress conditions. When we double the confining stress to 40 megapascals, we see here that the rock required something like 270 or 280 megapascals differential stress to reach its yield point and to produce a fracture. Thereafter, again, we find a very substantial drop to the level of sliding friction. Again, some minor strain hardening here, but essentially again a flat base of sliding friction here at just under 200 megapascals. When we go to higher confining stresses, we see here that the drop between the rupture point and the sliding friction level becomes smaller and smaller, and at very high confining stresses this drop disappears entirely. We reach a yield point, and thereafter we require the same high 360, 370 megapascal differential stress in order to cause sliding friction along these shear planes that form under these high confining stresses. The disappearance of the drop after the confining stress is also typical for ductile failure. Under these conditions, in the ductile field or at very high confining stresses, the angle between the shear plane and sigma 1 is at about 45 degrees. In the brittle field, the maximum is about 30 degrees, perhaps 35 degrees, depending on rock type. So in summary, we can say that increasing confining stress increases the shear strength of rocks. It decreases the difference between the failure conditions and the differential stress that is required for sliding friction. At the same time, we see that at low confining stresses we have substantial barreling, and we form tensile fractures, mode 1 tensile fractures parallel to sigma 1. With increasing confining stress, the fractures become increasingly oblique to sigma 1, and in transitional tensile failure conditions they have a component of tensile opening and of lateral shearing, but with higher and higher confining stress we will find fractures that only slide the rock fragments past each other without any component of tensile opening. And such fractures in the brittle field are typically around 30 degrees with respect to sigma 1. In the ductile field, this angle increases to 45 degrees with respect to sigma 1. These are the most important characteristics of fractures under increasing stress conditions, which correlate to increasing depth in the Earth's crust. And we are going to talk about these features in some more detail in the next chapter, where we deal with the more stress diagram. Thank you very much.